there is a water table on Mars. And actually we see sometimes that liquid water emerge on the surface in springs. And Mars definitely was habitable in the past. But as time goes on, I think many of us are starting to think more about trying to get ourselves in the shoes of an alien. What 1,000 years from now, 1,000,000 years from now, how will we be communicating across interstellar distances?
While we can't predict the future, we can make some guesses about life beyond our planet. In this episode, we'll explore how new innovations are helping to unlock this mystery. Big questions, no easy answers. Dive into the mysteries of the universe with Unknowns. From the secrets of the Big Bang to the future of humanity. Discover what we still don't know. Tune in and explore the unknown. Hi, I'm Kim Lochner and I'll be your Unknowns guide. Our host is David Christian, a historian, the founder of Big History, and the host of the Unknowns podcast. And our guest today is David Flannery, an associate professor in the School of Earth and Atmospheric Sciences at Queensland University in Brisbane. David's research focuses on astrobiology, geology, aerospace engineering, and astronomic sciences. He also worked for several years with NASA and the Jet Propulsion Laboratory in Los Angeles.
So how do astronomers and astrobiologists go about the task of searching for whether we're alone in the universe, whether life exists elsewhere? Let's focus on this question of whether there's life elsewhere.
We could start with Earth, our own planet, because if we'd like to understand, well, first we need to understand what we're looking for, I guess. So to understand the history of life on Earth is very important. So many astrobiologists are focused on that and on the geological record, like myself, also on the early evolution of life and whether there are other examples of an origin of life, a separate origin. So not a different branch on our tree of life, but a separate origin altogether. Did that happen more than once on Earth? I mean, we have a sample size of 1, but we need to increase that to have a statistically significant view. Another way people go about this is by looking at the available real estate. So we could look for planets orbiting other stars, exoplanets. And there's been a huge amount of progress in that field, just in my lifetime, actually. When I was, say, in primary school, I could go outside and look at the night sky and look at all of those stars and not know whether any of them had solar systems like our own. And it wasn't just me, actually, it was scientists. Many of us thought that actually maybe our solar system was rather special and that planets, especially rocky planets like Earth, were extremely rare. But in the mid-1990s, we found our first exoplanet, and now we know of many, many thousands of them. Some of them seem similar to the Earth. We could also look for a second origin of life beyond Earth in our own solar system, perhaps in an environment that's remained separate throughout the entire history of the solar system. Some of the most exciting places are Mars, which I can tell you a lot about today. Also, Venus is much harder to explore, and other less familiar habitats in our solar system. For example, the oceans under the ice on moons orbiting Saturn and Jupiter in the outer solar system.
If you had to make a bet on whether there is life elsewhere, either in the solar system or elsewhere in the galaxy or the universe, what would your bet be?
So I often ask this, and I'm afraid I don't know. And that's exactly why I'm interested and I spend my time on this field of study. But I do think that within my own lifetime, we will have some answers, at least to the question of whether life evolved beyond Earth in our own solar system.
So this is a mystery that you're reasonably confident we may get some good answers to within a few decades.
Yes, we already have some constraints around SETI, but it's a much larger space that's much harder to explore. Whereas our own solar system, we have habitable environments on Mars now. So we know that these were places where life as we know it, the scum living in the pond outside this room in Centennial Park in Sydney, you could have thrown that into one of these lakes on very early Mars. And as far as we can tell, it ought to have had a great time there. So if we don't find evidence for life in those ancient environments, well, why is that?
It would mean that planet Earth was a very, very special place, wouldn't it?
Could do.
Let's focus on the evidence from the solar system. Where are the most promising places to look within the solar system for evidence that life may have evolved elsewhere?
It might help to differentiate our search for life into two different categories. Life existing right now, extant life. And there are some places beyond Earth where we might assume that life as we know it, and I'm talking about life as we know it, not some sort of hypothetical alien life based on a different system, different biochemical system. And some of those places include Mars in the subsurface. I'll explain why the surface of Mars isn't really habitable today, but definitely the aquifers in Mars under the surface on Mars could be habitable today. Also, some of these oceans in Enceladus and Europa, these icy moons orbiting some gas giants, they could be places where life has a solvent like water, it has an energy source, and they're not too deadly. So there are places that we can go right now, and we are starting to go there to look for living organisms. But my own search for life focuses on the geological record, the very early geological record of Earth, but also Mars. And I'd love to investigate Venus as well. And that's because billions of years ago, let's say 4 billion years ago, both Earth and Mars, and maybe also Venus, probably had dense atmospheres. They probably had liquid water on the surface, rivers, lakes, maybe even oceans. And they could have all been green. They could have all been inhabited by microbial life.
In big history, we tend to talk about increasing complexity. I mean, that's one of the central themes of big history. And when we talk about increasing complexity, we ask about the ingredients that are necessary for increasing complexity and the Goldilocks condition. So I think what you've just said is that it's not just Earth in our solar system, but several of the planets in our solar system may have had at one time some of the ingredients and some of the Goldilocks conditions, and they may even have them right now. Is that correct?
That is correct. And so if we don't find life originated in any of these other environments, I guess we have to ask ourselves, what is so special about our own origins on this planet?
Yeah.
And unfortunately, on our own planet, we can't see far enough back in the geological record. We can see back a really long way, but our oldest rocks are about 4 billion years old. The planet is about 4.5 billion years old. So there's 500 million years there that we have no visibility into. And it's in that time period that life seems to have originated somehow on this planet.
On Mars, can we look that far back? Because you said you're a geologist. Is it possible on Mars, do you think?
It is. And that's why Mars, one of the reasons Mars is really interesting. See, on Earth, we have a living planet, which is great because it's one of these superorganisms. We, as the animated portions of the Earth's crust, sometimes I think we're just rocks that are moving around and
living rocks.
Yes, we're sort of changing and affecting the biosphere and the geosphere and the atmosphere, but it's all the same system. And it's able to continue going over geological timescales because we have this constant exchange. Like, for example, the carbon cycle. We're made of carbon and gets put in the atmosphere, gets sequestered in the rocks, in the geosphere, and it goes around. And it's able to do that because our planet is alive, including in the sense that we have plate tectonics. We have this constant recycling of rocks. That means the surface of our planet is constantly being destroyed and recreated. Luckily, there are some rocks that still remain from these very early time periods. But as we go further back in time, there's fewer and fewer of them. Mars, in contrast, has been dead in some sense. Not totally dead. There's still things happening, volcanism and other things. But that recycling of rock through plate tectonics, if it ever happened, it ceased many billions of years ago.
So there is no plate tectonics now on Mars?
Not in the sense that we have this subduction and recycling of rocks on Earth. And so that means that you might have a rock that was created 4 billion years ago on Mars, and it's just been sitting there on the surface. It's perfectly preserved from a geologist's perspective.
So from some points of view, Mars is maybe an easier place to look for ancient life than Earth.
Absolutely. If you're interested in the origin of life or the earliest phase of the evolution of the solar system, you need to go to Mars to ask that question.
What about Venus?
Venus, very rarely talked about because it's so difficult to work there. The spacecraft we send, they only endure a few hours. We essentially bring, it's almost like ice, a phase change material that slowly melts and allows the spacecraft to stay cool enough for materials that we work with, including for computers, to remain operable. So we know a little bit, but we don't know very much. What we do know is that there's a difference in the crust on Venus that looks sort of similar to the continents we have on Earth. There may be very old parts of the Venusian crust that I would love to investigate.
So what have been the crucial steps in looking for life on Mars?
I think it's always been a really interesting object in the night sky. It's red, it's rather large, it's a star or planet, which means it wanders through the night sky. And so we've wondered about it for a long time. And with some of our first telescopes, we turned them towards Mars. And although we couldn't see much, we could see a crustal dichotomy, and so a difference in the northern and southern hemispheres of Mars, and we could see the polar ice caps. And so even hundreds of years ago, astronomers knew, wow, this is a really interesting place. And it was common for a long time, all the way up into the 1960s, to look at those features through those telescopes, make maps of the surface of Mars, and a lot of people interpreted those features as evidence of perhaps even intelligent civilizations. And this was a very popular idea, maybe even the prevailing view, right up until we sent our first spacecraft to Mars. It was built at the Jet Propulsion Laboratory. It was a flyby mission called Mariner 4. So it flew by Mars very quickly, and it snapped a few photos. And I can imagine what the atmosphere would have been like at that time when those grainy black and white images came through. People were probably hoping to see canals made by aliens, or at least maybe some evidence of a biosphere.
But no cities. They saw no cities.
Well, not even a blade of grass. In fact, it looked pockmarked with craters. We've discovered it had a very thin atmosphere, no appreciable magnetic field. And so people were quite disappointed. But over the years, as we had follow-on missions that inserted themselves into orbit, took a lot more high-resolution images of many different parts of the Martian surface, we realized Mars is actually still pretty interesting. Unlike any other planet in the solar system, except for Earth, geomorphologically, we have the highest mountains in the solar system on Mars, the deepest canyons, active volcanism, and features that have definitely been carved by large amounts of liquid water moving over the surface at some point.
So we don't see rivers now, but we see plenty of evidence that they used to be rivers.
And not just little creeks, big rivers, hundreds of times bigger than the biggest rivers on Earth today. And there's still water on Mars that's just locked up as ice. And so in the 1970s, NASA and the global science community still thought it may be possible to find living organisms on the surface of Mars. And so when I think back to it now, it was an amazing achievement. Just about 10 years after that first mission flew past Mars and off into the outer solar system, NASA sent the Viking mission, which were 2 orbiters and landers, all operated perfectly. The landers, one of them landed in a higher latitude in a colder environment, and the other closer to the tropics, if you can call the equator of Mars the tropics. It's still very cold, like maybe 100 degrees Celsius below zero. And both of those landers scooped up the regolith, the soil, and looked for evidence of active microbial metabolisms. And although the results at the time were a little bit hard to interpret and controversial, over the years and decades we realized the surface of Mars is not habitable for life today, in part because the soil contains perchlorates, which is essentially bleach. And so any sort of microbes that are hanging out there would be destroyed quite quickly.
So if you go lower?
That's a very interesting question. So the surface is no good anymore, but there is a water table on Mars. And actually we see sometimes that liquid water emerge on the surface in springs. We see this like right before our eyes happening live from orbit. We have some great cameras looking at the Martian surface. And so all of that water rapidly turns to a vapor, and any life in the water wouldn't be able to reproduce, at least on the surface. There could be an active biosphere in the subsurface.
Still alive today?
I think it's reasonable to assume.
Right.
Imagine the Earth, for example, as far down as we drill into our own planet, even if we're starting at the bottom of the ocean and we go 5 kilometers down in solid rock, we bring up samples. It's teeming with microbial life. And so imagine Earth was hit by a huge asteroid and we boiled the oceans down to the seafloor. You couldn't sterilize the Earth. with any conceivable event. It's impossible. So I think if life evolved on Mars, microbial life like we have on Earth, it's reasonable to assume it may still be there.
So what's the most latest research on life on Mars?
Well, after Viking, there was a bit of a pause as we were a bit disappointed. I think the astrobiologists, okay, there's no life on Mars today. But as we learn more and more about the distant past, we got really exciting images of the rivers and lakes and things that existed in the past. We thought, maybe we can go and look for fossil evidence of life from this much earlier time period. And that's what we've been doing on Earth since the 1950s. We've been looking back as far as we can. And it turns out in pretty much every environment that's preserved in our record where life could have existed on Earth, we find abundant evidence for it. So why don't we go to Mars and look for the same evidence? And that's what we're doing right now on Mars with the Perseverance rover mission. It was launched in 2020. I was working at JPL in the lead up to it, and we were thinking about what instrumentation we would need on this rover. And it was really exciting because this is the first mission since Viking that's actually been tasked with this goal of looking for life. It's the first mission in a long time doing that. But of course, we're not looking for living organisms alive today. We're looking for the fossils. And so we tried to equip the rover with fieldable versions of what we use in the laboratory back on Earth. That mission also has another really important goal, which is to take samples of the rocks that we think are most likely to preserve that evidence of life and stick them in a cache and hopefully bring them back to Earth in the near future. I'm talking maybe 10, at most 20 years from now.
Right. So we may have Mars rocks on Earth that we can study in a lab on Earth.
Exactly. And we should find evidence for life if these environments were habitable. And so Perseverance has been operating for a few years on Mars now. We landed at the bottom of a crater called Jezero Crater, which we understand was full of water up to the brim at some point in the past. We can see where the water flowed in a big river channel, and we can see where it breached the rim of the crater and flowed out, maybe into a global ocean, something like 4 billion years ago.
4 billion years ago.
Yes, it's a big number, but the rocks look like yesterday's rocks, which is great. And so we landed at the bottom of this crater on what we thought would contain or preserve the sedimentary rocks that were created at the very bottom of this lake, where all the microbes and clay should rain down and lock in that evidence. Much to our surprise, we didn't find sedimentary rocks at all. We found volcanic rocks, lava flow, which was a bit of a disappointment at the time, but it allowed us to collect a sample that will date the entire succession because we can use radiometric dating methods. We can use isotopes essentially to date those volcanic rocks. So that was a few years ago. Since then, we've moved up to the edge of the crater. We've found those sedimentary rocks. We've found a whole bunch of really exciting minerals that preserve that evidence for past life. Talking about minerals that like calcium carbonates that bones are made of, and silica, which can preserve individual microbial cells if they were present. And we've now moved up and out of the crater, and we're looking at the much older rocks just outside the crater. And so we're having a really awesome cache of exciting samples to bring back to Earth.
Can I ask very quickly if there's any chance of life having been swapped between Earth and Mars? Because I know that there are meteorites on Earth that arrived from Mars. They were kind of kicked up from Mars and they flew here. And some people have claimed that even they may contain evidence of life.
That is such.
So, I mean,
question.
could life on Earth and Mars actually be the same life?
Could be. If I can step back to the first part of your question, I think you're touching on something that is often called the Drake equation. So we're trying to figure out how common life might be beyond Earth. It's not really an equation, it's more of a thought experiment. And one of the first variables in the so-called equation is the amount of real estate. So how many planets are out there that are like Earth? We have a really good understanding now. We've made a lot of progress. Okay, there's heaps of real estate. The next question is how many of those planets that are habitable did life actually start on? So obviously life started on Earth. We're having this conversation right now. We want to increase our sample size, and so we need to go to these other habitable environments. And we now know, thanks to these Mars rover missions, that Mars definitely was habitable in the past. So we're getting really close there. If we find life in those habitable environments, I think the next question is exactly the one you asked. Is this a separate tree of life, or is it the same one? Because we do have our only samples of Mars, actually, and we get to work with them in our laboratories, they've come naturally as meteorites. And it's conceivable that in some of these very large impacts, you could transfer microbial life between the planets.
Can we look at other planets in our solar system? And what evidence do we have about the likelihood of, and we talk about bacterial life, really, aren't we, on other planets in our solar system?
We are. We're talking about microbial life, and there's a good reason for that. On Earth, for most of our planet's history, the planet was inhabited exclusively by microbial life. And although sometimes we like to make a distinction between microbial life and complex life, microbial life is definitely not simple. Most of the cellular machinery, most of the metabolisms that keep our planet habitable, most of you, in fact, is actually not you, made up of these microbes.
So I'm like a huge crowd of microbes.
You are, and they're performing most of the work.
Michael Archer in another podcast talked about the bioblob.
Yes, we are the bioblob.
We're part of the, we're just tiny leaves on the bioblob.
Yes, and so we show up quite late in Earth's history. And so, of course, if we're looking elsewhere, beyond Earth or in our own solar system, even different solar systems, we should probably focus first on that microbial life. And there are places in the solar system, I think we've touched upon a few of them. The subsurface of Mars, life could, as we know it, could exist there right now. And we're just starting to explore these oceans that exist in the outer solar system. They're way too far away from the sun to be kept warm enough by solar radiation. But because they're close to these massive gas giants, tidal forces, just the flexing of the crust is actually able to keep those moons warm enough for liquid water to exist.
So that would provide one of the vital ingredients for life to exist, which is a source of energy or warmth or...
Yes, life needs...
Even though they're so far from the sun.
Exactly. And so when we start thinking about life in those environments, we have to expand our search space, I think. Classically, we look for life on planets like Earth in the so-called habitable zone, so not too far away from the sun. We can't keep the planet warm enough, but not too close that the atmosphere boils off or it gets hellishly hot like Venus. But if we think more carefully, I think we realize that it's more complicated than that. You could keep a planet warmer further away from the sun. If it had a biosphere, maybe it could maintain habitable conditions and more carbon dioxide and other greenhouse gases in the atmosphere. And even if we look way out in our own solar system, out to Saturn, there are moons which may satisfy these conditions. So we have water. We need water as that solvent, liquid water, and we need an energy source. And we have both of those, say, in the subsurface ocean of Enceladus. Heaps of water.
Enceladus, which is orbiting which planet?
Saturn.
Saturn.
So we have, at the surface is frozen, but we can see that ice has been fractured not too long ago, geologically speaking. We can actually see water coming out in plumes. We have missions in the pipeline to go and sort of sniff those plumes for evidence of life.
Have we got satellites heading towards Enceladus right now?
Not right now, but we do have a mission. We'll be headed towards Europa.
Europa, right.
Which is a similar moon orbiting Jupiter, which has an ocean below a frozen ice exterior. And in both of those locations, towards the middle, underneath that ocean, there's probably a solid rock core, which could be quite hot because of this tidal forcing. And so we might have communities that could be similar if we imagine the bottom of Earth's ocean where hydrothermal vents are emitting both the heat, but also a whole bunch of different minerals and elements in different oxidation states that microbes love to use as energy sources. Maybe there could be something similar down there. Be very hard to get to, though.
Yeah, but we could get evidence within a decade or two about...
First missions will go and orbit some of those moons, and we can access some of the material that's making its way from the ocean into the atmosphere. That's really hard, but that's happening soon. The next step is to actually land on the surface. There was a component of the Europa mission that intended to land on the surface. It's been cancelled recently, but I'm sure there'll be more. The latest concept is this Enceladus Orbi lander mission. But in the even more distant future, we hopefully will access those subsurface oceans, and it's technically very difficult. And of course, we would contaminate them probably as soon as we looked. So hopefully we do a good job.
Other lines of research that you think might yield more answers in the next decade or two about the existence of life beyond the solar system?
I guess we've been looking at radio waves for a long time, and we started off looking for narrowband signals. So just a really simple tone, essentially, like it doesn't really convey any information. It's just sort of, I am here. But as time goes on, I think many of us are starting to think more about trying to get ourselves in the shoes of an alien intelligence that may, say, intentionally want to communicate with us. I think that's a really interesting avenue of investigation, because unintentional signals may be much harder to detect. But we're starting to look around our galaxy, and we are starting to catalogue the Earth-like planets. If we had 1 million years to do this, and there's a lot of time available, it's been around for billions of years, I imagine we might build a catalogue of every single Earth-like planet in the galaxy, sort of keep our eyes on it. And if we wanted to, we could target transmissions. We could even send spacecraft to every Earth-like planet if we wanted to. And how would you send those signals? Well, you're probably not going to send just a simple tone. At least I wouldn't. I'd want to send some information. And what does information look like? Well, these days, the information that comes, say, from our mobile phones, it looks a lot like noise, because it's much more complicated and it's sent as efficiently as possible. So there's an interesting question. Would we even recognize these transmissions?
Yeah. Before we start talking about the future of humanity in space, just one more question which is really about SETI. What has SETI found so far? I'm guessing most of what they've found is negative. And what do they conclude about the likelihood of us finding aliens we can talk to?
I know you're probably going to get sick of me saying this, but I don't know, which makes it really interesting.
No, this is absolutely what these podcasts are about.
The SETI folks haven't found any convincing evidence for life beyond Earth. A lot of exciting data that's been analysed extensively and I guess could be related to some sort of transmission from an intelligence beyond Earth, but nothing really convincing enough to get us excited. But as I mentioned, we're just sort of scratching the surface, and what we started looking for in the 1960s really isn't relevant now. For example, the Deep Space Network that we use to communicate with, say, Mars rovers and other spacecraft in our own solar system, NASA has plans to convert that to an optical system. So we'd use directed beams of light to communicate larger amounts of information more efficiently. That will be much harder to detect unless that light beam was aimed directly at you. In other words, we're looking for completely different things now than we were in the 60s.
Yeah.
What 1,000 years from now, 1 million years from now, how will we be communicating across interstellar distances? Could be totally different.
Perhaps now is the time to talk briefly about the Fermi paradox, which is really, I guess, linked to an earlier era of research into life beyond the solar system. And my understanding is that the Fermi paradox arises from the failure of SETI to find any signals. So that raises the question, does that mean we're alone? If so, why are there no intelligent aliens out there apparently? Have I got that right?
No, I think you've got the essence of it there, and it was a really obscure concept until recently. Now it's become quite popular, which I think is great. And the essence of it is exactly as you just described. It's really quiet out there. And so there's a few possibilities, I guess. The first possibility that sort of my research can be focused on is how common is it for life to arise from non-life on an Earth-like planet? And then how common is it for an intelligent organism to evolve from that simpler microbial life?
Yeah.
It seems to have been a bottleneck on Earth. Life got started fairly early, within the first 500 million years, but it took 4.5 billion years for you and I to have this conversation.
And I gather one of the interesting things about the Fermi paradox is this line of speculation that says, if we haven't found aliens out there, is it possible that whenever you get a really smart or really intelligent species around any star system, it outsmarts itself and destroys itself? That's, I know, one of the lines of speculation associated with the Fermi paradox. Do you have any strong views about that?
Well, it's
the bottleneck.
It's quite grim, actually, and it's one of my favorite answers to the question. But it's just one, actually, and it's only possible to even consider this possibility because of the time aspect.
Yeah.
We've got a huge amount of time to work with. Well, there's a few possibilities. Maybe that first organism constructing itself on our planet, maybe that was the product of such an unlikely confluence of coincidences. It's happened only once in the entire history of our solar system. Maybe it's only happened once in the entire history of the galaxy.
And that makes us incredibly significant.
Well, absolutely.
Yeah.
And we'll know if we find life on Mars, obviously, whether that's the case. But I think so we have to start with that working hypothesis. We really don't know. A lot of us have a gut feeling that life should be common, but maybe it's extremely uncommon. There's your answer to the Fermi paradox right there. If life's common and intelligent life evolves, not commonly, but every now and again, it's possible that it evolves so spaced out along that time spectrum. Maybe intelligent life evolves only every few 100 million years. We'd never have the opportunity to communicate with each other unless our civilizations endured for millions or hundreds of millions of years. What are the chances of that?
Yeah.
I mean, I'd be happy if we last another 100 or 1,000 years.
Yeah. Now, I'd like to shift ground a bit. So these are questions about the likelihood of us migrating beyond Earth, first in our solar system, and then I'll ask about beyond. What are the chances, do you think?
I think space is fundamentally different to the surface of the Earth. That's the first point I'd like to make. And we did do a great job of colonizing the surface of our planet throughout our human evolution. But the living space in space is fundamentally different. And so I think the exploration of space with humans will have to be driven by some really powerful factors, maybe economic factors, perhaps even religious factors, but they'll need to be there because humans are not good at living in space. Well, we could start with the best place. This is the best places to go. So if you want to live beyond Earth, Mars looks pretty good. It's a planet that has a surface, got water. It's sort of similar to Earth. A lot of people talk about the colonization of Mars. Maybe we can make it like another Earth. But there are a few things to consider. We could start by thinking about just getting there in the first place. So say you wanted to travel to Mars, and this I think is something that will happen maybe within our lifetimes. Humans will go to Mars. I don't think we're going to stay very long.
Humans will go to Mars.
I think so.
Within a decade or two.
I think it's likely, and it's going to be driven by geopolitical issues and drivers and competition between nation states on Earth. If we want to do the science, honestly, we could send the robots. And it's a slightly controversial opinion I may have here, but I think if we were going to spend hundreds of billions of dollars, that's what it would cost to send humans, keep them alive long enough to plant a flag on Mars, we could do a lot of really good science robotically. So it's not going to be science that will drive this. We'll do some great science, I hope, on the coattails of the human exploration programs. But if we send a human, let's say, to be the first to create that presence or plant that flag, what would it be like to be that human? Well, you're going to have to put yourself in a fairly small spaceship, and you're going to have to spend many months on the way to Mars. And along the way, you'll be irradiated fairly substantially. You'll receive, just from the cosmic background, not even from the sun, you'll receive something like your annual background radiation dose on Earth every single day. You'll increase your chances of getting some sort of cancer in the future, and you may actually get sick when you arrive on Mars. On the surface, you'll be receiving a similar radiation dose. If the sun decides to have a hiccup, you'll have a much larger issue. You might die. Okay, so that's the radiation environment. It's not very nice, particularly if you wanted to live on Mars longer term. You wouldn't be able to spend much time on the surface. You'd need some sort of shielding, which you might conceivably develop on Mars, but in transit, it's much harder. But let's say you get there and you stay for 1 Mars year, perhaps. On the surface, you'll be continued to be subjected to that radiation environment. You'll also have to deal with a constant flux, this constant rain of micrometeorites, which could erode your spacesuit, which could be a problem because you're going to have to wear that spacesuit all the time. You're never going to be able to take it off outside because the Martian atmosphere is about 100 times less dense. There's no oxygen in it to breathe. And it's also really, really, really cold, like 100 degrees Celsius below zero. And every day when the sun comes up, that temperature could change 100 degrees. So it's not a nice place to live from the radiation environment, the temperature, the meteorite flux. You've also got to consider the soil. You might want to grow some potatoes or something while you're there. But that soil, as we mentioned earlier, is full of these toxic compounds like bleach. And you'll also be separated, it occurs to me, if I think about going myself, from every other human and from the Earth by this very large distance, which means you might want to plug into the internet, but it's going to be a very laggy connection. So I think it's, in the near term, it's going to be difficult, but definitely achievable to go there with humans.
Are there any more attractive environments in our solar system?
Well, maybe if we think about the longer term, say colonization of Mars, is perhaps even harder in one sense, because if we wanted to make a place like Mars like the Earth, for example, let's get rid of this
terraforming.
Terraforming. Let's think really big. This is the podcast about big ideas and big timescales. So let's imagine we've got near infinite resources and time. What can we do?
We're going to turn it into a 5-star hotel.
Let's turn it into a 5-star hotel. Let's make the flowers grow. Let's give it an atmosphere. Let's imagine what that would be like. So we want to fill the atmosphere with enough greenhouse gas and some oxygen for us to exist, for it to be warm enough and breathable. Well, there are some materials in the ice caps. There's water ice, there's carbon dioxide ice. Let's get that into the atmosphere. It would require a huge amount of energy, but it could be done. It won't last forever, though. And the reason for that is the same reason Mars doesn't have much of an atmosphere today. It probably did in the past, we think, but it's been stripped away. How? Well, Mars doesn't have a magnetic field like the Earth, an appreciable, a strong magnetic field, which means that the gases in the atmosphere over geological time periods, they get stripped away. And one example of how this happens is that the water vapor in the atmosphere, when radiation interacts with the molecule, turns it into free hydrogen and free oxygen. The hydrogen's very light, and so it floats away up into the upper atmosphere and it gets stripped away by the solar wind. And eventually that takes away all of your water in the atmosphere. So could we give Mars a magnetic field to prevent this from happening? I don't think so, because magnetic fields seem to have something to do with the interaction between solid and liquid metal cores in rocky planets. And the Earth is actually the only planet in our inner solar system that has a strong magnetic field. Mercury doesn't have one, Venus doesn't have one, Mars doesn't really have one. So could we create one? Well, no, we need a new planet, really.
Oh my gosh. So not only is it not a 5-star hotel, if we manage briefly to turn it into a 5-star hotel, pretty quickly it would cease to be a 5-star hotel again.
Not if I play the devil's advocate to my own response there, say we got really good at creating our own habitats. I mean, that's conceivable. Maybe we could dig a hole on Mars and underground we could have a self-sustaining, entirely like recycling, sort of Star Trek-like environment. I think that's conceivable, given infinite time and enough resources. But if we could do that, I have to wonder, why Mars?
Yeah.
Why not the moon? Why not, say, the International Space Station exists within our own magnetosphere, so you'd be shielded from radiation there? Why not the bottom of the ocean on Earth? Why don't people live there? I think the answer is that they're not very nice places to live.
Yeah. So what are the possibilities that, even in a fairly squishy form, humans or our descendants, perhaps with some modifications, will make it to nearby star systems? Let's give a figure, let's say within the next 1,000 years.
I think it's definitely possible. If we're thinking about much beyond our local environment, like hundreds of light years away or thousands of light years away, it's going to take much, much longer, simply because of the vast distances involved. But even the nearest star, the technologies that we would require, we can conceive of them, but it's nowhere near within our grasp. We might first send very small computers with something like a solar sail, which we're able to accelerate in that direction, just to fly by those star systems and maybe snap a few photos or collect some data. Eventually we could maybe send ourselves, but I can't get over this question of why. Like, why don't we live at the bottom of the ocean now or in a hollowed out asteroid in the future?
Our next episode is about all things Big History, as we reflect on over a decade of Big History project and what the future might hold. Check out the other episodes of Unknowns, where we explore mysteries and questions about our origins and our future. Interested in learning more about Big History? Check out the Big History Project, a free online course for middle school and junior high students.